So the last bit of the geometric distribution topic is to look at one of our new topics in conjunction with it, which is, of course, the goodness of fit. So a chi-squared test to decide whether the data we observe fits the model that we think we've got. And, of course, that model could be anything, including a geometric distribution. So, again, straight in with an example. We've got here a large DVD collection, and Sarah's picking DVDs off the shelf until she finds one she would like to watch. So she's picking them off until one success. Great, definitely geometric distribution then. She thinks there's about a 50% chance she'll be in the mood to watch any particular DVD, and she apparently takes a record of these things. Again, just let the context roll over you. So calculate the expected frequencies if the number of DVDs considered is modelled with this particular geometric distribution. So essentially for each section, don't forget what we're saying is, okay, what's the probability that she picks first time? So that would be 0.5 multiplied by her expected number, which is 52, sorry, not her expected number, her total, to get the actual number of DVDs. So that's going to give us an expected value of 26. Probability that it takes her 2 DVDs before she finds one, so that's 50% for the one she doesn't want first, 50% for the one she wants second. Of course, then multiplied by your total frequency gives you 13. And so on and so forth. So 6.5 for the next one, and 6.5 for the remaining ones multiple, because she could keep picking forever and ever and ever, and we know that we need this total to add up to 52. So actually this one isn't just 4, it's anything that makes that total 52. So she wants to decide if her guess is a good one, her 50% chance, and we're doing that by comparing the observed frequencies to the expected frequencies. So in B, H0, well, the geometric is a good fit. And H1, the geometric is not a good fit. We'll calculate our x squared value. Don't forget that's the sum of the individual values squared over the expected value minus the total number. That's that alternative version of the equation there. So that's 33 squared over 26 and 12 squared over 13 and so on and so forth, minus the 52 that we've got, which is 5.423. None of our expected values are under 5, so I don't have to combine any of my columns. And so my degrees of freedom is my number of columns, which is 4, my number of cells that are interesting, take away 1, which gives me a degrees of freedom of 3. So if I look at the chi-squared family, 3 degrees of freedom at 5%, I get a critical value of 7.815. So now we are comparing our x squared value, which is 5.423, the kind of measure of difference between your expected and observed, and that is within my allowable value, which is given by the chi-squared value. And so we are saying here, do not reject H0. Evidence, well, what does that actually mean? So it's evidence that the observed values sufficiently fit the expected numbers. And so Sarah is right in her assumption. We've got no reason to disbelieve her. So you can see that it's working exactly like any other goodness of fit hypothesis test that you've ever done. The only difference is when calculating your expected values, you're doing so using that geometric distribution rather than any other version. Of course, we know that sometimes you don't have the value of P, and we need to be able to calculate it. So just to do one example where that is the case, and don't forget, if we've calculated P using our data, we need to knock an extra degree of freedom off, but we will do that when we get there. So Katie's flagging down taxis to take her home after work. She records how many taxis she tries to flag down before one stops. So there's the attempts before one success. That means that we know we are in a geometric distribution. So she thinks she can model the number of attempts using this geometric distribution, where we don't, though, know the probability. So don't forget, probability is at its root cause, it's the total number of successes out of the total number of attempts. So our probability then, well, she's successful 100 times, because eventually she does flag down a taxi every day to take her home. But how many attempts did that take her? Well, there were 76 occasions, where it only took her one attempt. 17 occasions where it took her two attempts, so there's two taxis in those days. 4 occasions where it took her 3 attempts. 2 occasions where it took her 4 attempts, and 1 occasion where it took her 5. So our probability then is 100 divided by the total number of attempts, which is 135, or 0.741. And so now we run our goodness of fit method to this, but of course we have calculated the probability, so we do need to knock an extra degree of freedom off. So we'd start with the geometrics of good distribution. Alternatively, it's not. We've got our observed numbers. We need our expected values now that we've got our frequency. And this one should be 74.1, this one 19.2, and then you get a whole load that you need to collect together, ultimately to 6.7, but those are going to combine those last 3 cells. Obviously, you could work this out. You could pause the video and just check in with me, but your x squared value ultimately ends up being 0.31423, so on and so forth. Our degrees of freedom, we've got 3 usable columns. We take our usual 1 degree of freedom off because the last cell is completely dictated, and we then must take this second one off because we used our own data to calculate P, and so our degrees of freedom is just 1. Our chi-squared value then at 2.5% is 5.024. And so our x squared values are smaller than our chi-squared values. So we are keeping our geometric for now. So do not reject H0. Sufficient evidence that this is a good model.